Look, props if you watched any of this at all. Much congratulations, even more if you watched the entire first video. I'd like to point out that we did 50 questions in about 43 minutes, which normally at Regents Review After School, we do 50 questions in 90 minutes. Now, technically, kids do get their time to finish it off before we actually go over the questions. I don't care. That's still impressive. We did a lot. Onward to part 2 and the short answers. All right, who's ready to do some short answers? No one raised their hands. Anyway, got to do it. Doesn't matter. 51. State the general trend in first ionization energy as the elements in period 3 are considered from left to right. This is great. They tell you period 3 or periodic table. You can go there and see what elements they are. It says left to right. Hopefully you all know what left to right means. No, not assuming anything here. We want to figure out what's the general trend in first ionization energy. Where do we find that? On table S, like everything else, we now know what elements we're looking for, and it says general trend. It's not interested in what happens from sodium to magnesium to aluminum. Overall, what happens to numbers? Just look at these actual numbers. What's going on? These numbers are going up as you're going from left to right. As you're going from element 11 to element 18, there's an overall rise. You may see it drop a little bit, like here between magnesium and aluminum, we see a little bit of drop before it bounces right back up again with silicon. But overall, you have an increase. So for number 51, I'm going to say that ionization energy increases left to right. Write an actual sentence. Don't write this shorthand like I'm doing. But ionization energy is going to increase from left to right. You don't need to write a complete sentence for this, but something like that. Number 52. Identify a type of strong intermolecular force that exists between water molecules but does not exist between carbon dioxide molecules. This is really just something you should be remembering. What is the thing that holds all these water molecules together so tightly? And that is hydrogen bonding. Remember, that's in molecules that have not only hydrogen, but fluorine, nitrogen, and oxygen. Remember, is hydrogen the only thing in hydrogen bonding? And the answer is F no. Fluorine, nitrogen, and oxygen. But in water, water has the hydrogen and oxygen. It's hydrogen bonding that holds water together so tightly. You could also say dipole attraction, dipole forces. None of you are going to say that. It's hydrogen bonding. Just write hydrogen bonding. 53. Draw a structural formula for 2-butanol. So draw the structure, draw the picture of 2-butanol. We just did organic chemistry. So we know we have all these little charts to use. Let me cross off my hydrogen bonding answer right here. And now we can use all these organic charts to figure out what the heck 2-butanol is going to mean. Well, again, I've been telling you for a week and a half. I guess really just a week. The name always gives you all the information you need. So bute. Bute tells us how many carbons at the beginning of the word. And bute right there tells me I'm going to have 4 carbons. So I'm going to draw 1, 2, 3, 4 carbons. The N, it looks like it would have been butane. So that means it's going to be all single bonds. It's an alkane. So I'm going to draw single bonds between my carbons. There's my 4 carbons. Single bond of that would have been butane, except for this little pesky ol at the end. And that ending to the name ol means there's some kind of functional group on it. So I need to go to our big table on the back of the periodic table and tell me, I guess that's the other side of the periodic table. It's across from this table R. And that's going to look like this alcohol. The name is on their side already. It says it would be propanol. And that means we have an OH somewhere. So I have to draw an OH group on this molecule somewhere. But how am I supposed to know where? Well, the number tells me exactly where. It's on the carbon number 2. So I've got carbon number 2 on either side. I'm going to read from left to right as always, and I'm going to put my OH right here. If you wanted to put on the second carbon from the right, that works too. I just find it easier to go that way. That's the only thing it tells me to do. So I'm now just going to draw a bunch of H's around. I'm going to draw little lines to make sure every carbon has 4 total bonds. And every carbon here does have 4 total bonds. If you want to go around and draw your little H's in, feel free to, but that takes extra time. So I'm only going to draw that many. You don't have to draw the H's. If you just draw the single lines, we know what's there. But you have to have your 4 carbons with all single bonds, and then the OH right there. That's the important thing on carbon number 2. That is 2-butanol. These next two, 54 and 55, are really great example questions of types of things you'll see in the Regents. It says you've got this little chart here. It says some compounds of silver are listed with their chemical formulas in the table. It gives silver carbonate, silver chloride, silver chloride, silver sulfate. The formula is not really important. Number 54 says explain in terms of element classification why silver chloride is an ionic compound in terms of, this is that packet we did in the review packet, or the document in the review packet. It says in terms of element classification, you could give a long-winded, really detailed explanation that answers why they're an ionic compound. But if you don't say in terms of element classification, we cannot give you points. In terms of the types of elements in silver chloride, this thing right here, Why is that an ionic compound? Well, what elements do we have? We've got Ag and Cl, and what types of elements are they? What do we know about ionic compounds? Ionic compounds are formed between metals, of which silver is a type, and nonmetals, of which chlorine is an example. So that's your answer. Silver is a metal, and chlorine is a nonmetal. You could talk about how the electronegativity difference is less than 1.7. You could talk about, or greater than 1.7 rather. You could say that electrons are passed back and forth from metal to nonmetal. Those things may be correctish, but it doesn't make a difference. Unless you say one is a metal, one's a nonmetal. You don't say which one's the metal, which one's the nonmetal. You're not getting points for this. So point that out because it says in terms of element classification. 55, show a numerical setup for calculating the percent composition by mass of silver in silver carbonate, which now I'm going to cross this off. Silver carbonate is this one up here, Ag2CO3. We're going to use that. Show a numerical setup. This is another great example question. Like I said, you don't have to actually do the math. You just have to show how you would do the math. So percent composition, we have that formula in the back page of the reference table. It says it's part over whole times 100. Silver carbonate. So it's saying the silver part of silver carbonate. So silver carbonate is Ag2CO3. We need part over whole times 100. The part, we're told, is the silver part, the mass of silver. So we need to know how much the silvers weigh. For that, we go to our reference table, and our periodic table tells us that each silver atom weighs 108 grams per mole. So there are 2 of them. So we have to account for that. So you could do 2 times 108, or just multiply it by 2 beforehand and get 216, however you want to set it up. But that's your top. And then the whole on the bottom is the entire molecule. And the question is nice enough to tell us that the entire molecule weighs 276. So I'm just going to write that right here, 276. Don't forget to times by 100, and that's all you have to do. Like I said, if you want to set up a little bit differently, if you instead of 2 times 108, you want to go ahead and do the math first and write 216 divided by 276 times 100, you could do that too. Yeah, either one of those things works, but that's all you have to do. Don't actually do the math, just set it up. 56, you're still using that chart, but it says identify the silver compound in the table that is most soluble in water. This is where table F comes in. Table F shows you things that are soluble or insoluble, and as I said to you during the chapter, there's nothing here that says this compound is more soluble than this one. There's no scale that like table J where it says it's a little bit more react in this one. The question that says most soluble just means it's going to be the only choice that actually is soluble, and all the other ones are going to be insoluble. So just go through these choices one at a time and then check table F and see where they fall. AgCO3, we have to find on our chart silver or CO3 and see where that is. I don't really see silver anywhere on the left side as listed as a soluble or insoluble compound, but I sure do see CO3. Carbonate is listed as something that's normally insoluble. So unless it has an exception, it does have some exceptions, but it says the exception is soluble when it's with a group 1 ion, which silver is not, or ammonium, which obviously silver is not. So silver carbonate is not going to be the soluble thing in water. Next one, silver chlorate. We already know now that silver is not on our chart, so let's just try to find the other part, the ClO3, the chlorate. And let's see, I see chlorate right here. Chlorate is listed as a compound that's usually soluble, unless it has an exception that reverses the rule and makes it insoluble, but there are no exceptions. So it sure looks like silver chlorate is going to be our option. I'm going to erase these things and go circle that in blue just so I know that that's the one I think is my answer. I'm going to circle it up here too. That looks pretty good so far. And let's just double check the other two. We're going to look for Cl, chloride, and sulfate, SO4. Chloride's right here. It's listed as one of the halides. And that also is normally listed as soluble, except silver is one of the exceptions, so it's going to make it insoluble. So it's not silver chloride, that'll be soluble. And sulfate is over on the bottom here. Sulfates, again, are listed as soluble compounds, except when combined with silver. So that's also going to inverse it and make that an insoluble compound. So silver chlorate is our answer. So this is identify the silver compound. So you could either write silver chlorate. You could write AgClO3. Either one's fine for a point. If you haven't noticed so far, in this part of the test, you have typically some kind of little chart or reading thing, and then a couple of different questions, usually of completely unrelated chemistry topics, all going to that one little reading or picture. In this one, it looks like it's going to be some kind of nuclear questions because it says a cobalt-59 atom is bombarded by a subatomic particle and a radioactive cobalt-60 now atom is produced. So it goes from cobalt-59 to cobalt-60, different versions of the same element. After 21.084 years, 1.2 grams of an original sample of cobalt-60 produced remains unchanged. So it looks like we're probably going to have some kind of half-life question. But let's see what they say as we go. Number 57 says, complete the nuclear equation by writing a notation for the missing particle. It doesn't say in your answer book. Typically it does, but you'll see because in your answer book, it looks like this. So you just have to fill in the missing pieces we've done a couple hundred times. So remember, we have to balance these things out. We can't lose any kind of mass. The mass on one side total has to add to the mass total on the other side. The atomic number on one side has to add to the atomic number on the other side. So if we go through this, on the bottom, on the right side there's only one piece, on the left side there's two. So let's start on the right. On the right side, our atomic number is 27. That means the atomic numbers on the left side have to add up to 27 also. The cobalt piece's atomic number already is 27. So what do you add to 27 to get 27 on the other side? Our missing piece has an atomic number of 0. On the right side, our mass is 60, which means the total of the atomic masses on the left side have to add up to 60. If the cobalt part has a mass of 59, what do we add to 59 to get to 60? And that's going to be a 1. So our missing piece has an atomic number of 0 and a mass of 1. How are we supposed to know what that is? Well, remember, you got the little secret table O that no one remembers is there, and that's really helpful here. We just need to find some kind of particle that has an atomic number of 0 and a mass of 1. Normally, our piece's atomic number would tell us to go to the periodic table and see what element it is. There's no element with atomic number 0, so we just have to find it on here. And right here in the middle of our chart, I see this little guy with an atomic number of 0 and a mass of 1, and that is a neutron. So if you shoot a neutron at a cobalt stable atom of cobalt-59, you can collide those things, and that turns into radioactive cobalt-60. So this little neutron right here is our answer for number 57. Number 58 says, based on table N now, identify the decay mode of cobalt-60. So the next two questions go back to that original reading passage. They're on different slides if you want to flip back and see it. Which says, based on table N, that is table N right here. What is the decay mode of cobalt-60? All you have to actually do is look up cobalt-60 and find what it says the decay mode is. Decay mode is right here. So your answer is beta particle. So you can either write the little fancy B with a minus, you can write beta, anything like that. You can write the little E with the -1 and the 0. Any of those that mean beta particle are good for that answer. 59 says, determine the mass of the original sample of cobalt-60 produced. So the question told us that after some amount of time, you had 1.2 grams of the original sample remaining. This now wants to say what was the original mass of the sample. So it told us in the question that it took 21.084 years total for the whole process to take place. On this chart now, we see cobalt-60, its actual half-life is 5.271 years. So I'm going to divide the total amount of time it took by the half-life time, and that's 5.271 years for each half-life. When I divide this, I see that it was equivalent to 4 half-lives. So it did 4 different divisions to be left with 1.20 grams of whatever we started with. So we're going to work backwards. We're going to have our half-lives here and our mass over here. We know we have to get to 4 different half-lives. After our fourth half-life, our fourth division, we know we're told that we were left with 1.20 grams remaining of the original sample. That means it would have divided 1 fewer time on step 3, so we're going to times that by 2, and we would have had 2.4 grams remaining. From 3 to 4, divide again, you got half of that, so we're going to work backwards now and multiply by 2 every time we go up. After 2 half-lives, we would have had double the 2.4, so we would have had 4.80 grams remaining. After 1 half-life, it would have been double that amount, so now we're up to 9.60 grams remaining. And after 0 half-lives, this is what I said was one of the trickier parts. Remember, you always have to go up to 0 to see what happened before anything took place. So 9.6 times 2 gives us a total mass to start out of 19.20 grams, and that is our original mass. We start with 19.2, and then we cut it in half 4 times, going to 9.6, 4.8, 2.4, and finally 1.2 grams. But our answer is the original amount, so that is the 9.2 or 9.20, either one. But that is our original mass of the cobalt-60. Next couple of questions refer to this little cooling curve here. And the wording here is important. It says a sample of a molecular substance starting as a gas at 206 degrees Celsius and 1 atmosphere is allowed to cool for 16 minutes with the process represented by the cooling curve below. So we've got this diagram here. It tells us it starts as a gas. So I'm going to go ahead and label that, because if it tells us it starts as a gas, that's going to be important. So starting at AB, that's where it's a gas. I've been telling you at the beginning of the year when we did this to label your pictures anyway. The diagonal portions are your one phase. So if we know we're starting as a gas, that's at this high temperature here, which means CD then is where it goes to a liquid, and EF is where it's a solid. Between B and C, it's going from a gas to a liquid. So we have a little bit of gas, a little bit of liquid, and changing proportions. Between D and E, it's going from a liquid to a solid. So again, we have two of the same, there's two different substances rather, two different phases. But at these three stages, we just have either all gas, all liquid, or all solid. Number 60 says, determine the number of minutes that the substance was in the liquid phase only. Liquid phase only means right in here, from 6 minutes to 11 minutes. We've got 10 minutes, we've got 12 minutes, so 11 right in the middle there. So how many minutes is that going from 6 to 11? And that's going to be 5 minutes. You could also just count. We've got one little section, 2, 3, 4, 5 between these 2 points. See, if you didn't know how to do the math, you got 5 little lines segments there. So 5 minutes. 61 says, compare the strength of the intermolecular forces within this substance at 180 degrees to the strength of the intermolecular forces within this substance at 120 degrees. Remember, intermolecular forces are the forces between molecules that hold them together. So the forces that hold a solid's atoms together really tightly, hold a liquid a little bit looser, and hold gas molecules basically not at all. So at 180 degrees, see right here, it's a gas. So we're talking really weak forces. It says we want to compare that to what happens, the forces at 120 degrees. So at 120 degrees, it's right here. It's a liquid. So they're a little bit stronger. So that's what you want to write. It says compare the strength of the intermolecular forces at 180, at 120. So I would say at 180, they're weak. At 120, they're stronger. You could just say more generally, they are weaker at 180 than at 120. You could say they're stronger at 120 than at 180. You'd say the liquid has the stronger forces, the gas has the weaker forces. They are stronger at the lower temperature and weaker at a higher temperature. Anything that means that, you're good for the points. 62 says, describe what happens to the potential energy and the average kinetic energy of the molecules in the sample during interval DE. So I'm going to erase some of these lines here because I want to have a clean area to write on. So just let me get rid of all this. And it says at interval DE, we want to look at potential energy and average kinetic energy. Well, thankfully, we know that average kinetic energy means what again? And everybody should be yelling at their screens, temperature. Why am I talking like this? I don't know. It's a long day. Temperature. So it's saying what happens to temperature during interval DE. And in interval DE right here, I see that nothing is happening to the temperature. So I'm going to write that my average kinetic energy is constant. You could write it's unchanging, however you want to word that, but constant is a good word. Constant temperature. Well, energy always has to be changing in some way. If temperature is not changing, if kinetic energy is not changing, the potential energy has to be. And because our temperature is always going down, our energy is always decreasing in a cooling curve. If the average kinetic energy is the one that's staying the same, then the potential energy is going to be the one that's changing, and that is decreasing. As we see, the energy is always going down. Remember, it's either potential or kinetic energy changing at all times. In a curve like this, a cooling curve, you're having always a decrease in energy. So either kinetic energy is staying the same and potential energy is decreasing, like in B, C, and DE, or you have kinetic energy going down and potential energy will be constant, like in AB, C, D, and EF. So potential energy here is decreasing because kinetic energy is constant. Just look for what's happening to the temperature, because that's the one you can clearly see on these curves. Potential energy doesn't tell you anything. Kinetic energy is temperature, so you can always see what's going on there. And if kinetic energy is not changing, potential energy has to be the one that is. So kinetic energy is constant, potential energy going down. 63 to 65, say it's this little picture here, and that looks like a piston. It looks almost like a bicycle pump with the hand pump. But it says the diagram below represents a cylinder with a movable piston containing 16 grams of oxygen gas, and at 298 K and 5.5 atmospheres, the O2 gas has a volume of 24.5 liters. So we got some information about this gas in this little chamber here.
Number 63 says, determine the number of moles of O2 gas in the cylinder, and the gram formula mass of O2 is 32 grams per mole. So they're nice, they give us some information again. It says determine the number of moles in the cylinder. All we know about it is that it's got this gram formula mass, and they tell us in the question, in the little reading thing, that we had 16 grams of the O2 gas. So that's more than enough information for us, because in our reference tables we have this numbers of moles formula. That is, the moles is equal to given mass over gram formula mass. So I'm just going to write this over to the side here, and I know that moles is the given mass. We're told we have 16 grams of it, so that's 16 grams up top, divided by the gram formula mass. That's how much 1 mole weighs. And the question was nice enough again to tell us this, that it is gram formula mass 32 grams per mole. If we were not given that, we could just add up how much O2 actually weighs. Each oxygen is 16 grams per mole, so because there's 2 oxygens, it would be 32 grams per mole. We didn't have to do that because the question told us, and that is how we figure this out. It says determine the number, so it's not just state how we'd set up, show how numerical setup for this. We have to actually do the math. So moles is going to be equal to 16 over 32, and when we do 16 divided by 32, we get an answer of 0.5 moles. So you could do it as 0.5, you could do 0.50, 0.500. In the question, they do have everything to 3 significant figures. So if you did 0.500, that's fine. But just basically 0.5 is what you're looking for. So a half mole. Number 64 now says, state the changes in both pressure and temperature of the gas in the cylinder that would increase the frequency of collisions between the O2 molecules. So what could you do to pressure to make the molecules of gas hit each other more? And what could you do to temperature to have the particles of gas hit each other more? So let's go one at a time. Pressure. What could you do to the pressure in this little tube here, in this cylinder, to make the particles hit each other more? How are you going to get them closer to each other and force them together? To do that, we can increase pressure. Remember, pressure only changes how gases work. They don't really affect solids or liquids when we have pressure changes. But you could increase the pressure on here. You could do that by actually pushing this piston down. If you could, some other way, kind of decrease the volume and make it a smaller thing, that's going to make the particles get really, really close to each other. But increasing the pressure will make the particles hit each other more. You could also say just make the pressure more than 0.5 atmospheres. You could be more general and say just increase it. You could also say that because you know the pressure as of right now is 0.5 atmospheres, you could say we'll just raise the pressure something more than 0.5 atmospheres, either one. For temperature, same kind of thing. How can we make these molecules hit each other more? That's, once again, just increasing the temperature. If you heat it up, they're going to speed up, they're going to hit each other more and have more collisions. So once again, you could be more general and just say increase temperature, or you can get a little more specific and say normally it's at 298 K. It tells us right now it's at 298 K. So the pressure, just raise the pressure to something over 298 K. I like just the very general increase because that makes it really easy for me to grade when I'm looking at your papers. Last question from this diagram with the piston and the gases. It has the same little reading thing, and now it just says show a numerical setup for calculating the volume of O2 gas in the cylinder at 265 K and 1 atmosphere. Now this one does say show a numerical setup, so this is one of those questions where you don't actually have to do the math, you just have to show how you would do the math, set it up properly. And it says we're going to calculate the volume of O2 at these conditions of 265 K and 1 atmosphere pressure. We don't have a formula for just tell me what the volume is going to be at these conditions, so you have to compare it to something else. So we do have up top here a temperature, a pressure, and a volume for our gas under these conditions initially, and now it's telling us we want to change that to 265 K and 1 atmosphere. So there's a new pressure right there, here's a new temperature right here. So for this, we're going to use this combined gas law equation. P1V1 over T1 equals P2V2 over T2. The pressure and the volume divided by the temperature at the first set of conditions equals pressure times volume divided by temperature at a second set of conditions. So to set this up, I'm just going to use my numbers here. The pressure from the initial set of conditions is up here. So that was 0.5 atmospheres. I'm writing the units in. You don't have to actually use the units because you're not going to really use them for the math anyway. But 0.5 atmospheres times the volume, which it tells us is 24.5 liters. Oh, messed that up. 24.5 divided by the initial temperature, which it tells us was 298 K to start out. That's now going to be equal to P2V2 over T2. So the pressure in the new condition, it tells us right here now, is 1 atmosphere We went from 0.5 atmospheres down to 1 atmosphere times V2, which we're calculating the volume. We're looking for the volume, so we don't know what V2 is. I'm going to leave that just as V2. And then we're going to divide that by the new temperature, which this tells us in this question is 265 K. Remember, temperatures need to be in Kelvin if you're going to be doing this kind of calculation. Question gives us the temperatures in Kelvin, so we don't have to actually convert anything. Otherwise, we would just add 273 to Celsius temperature. But we have this set up here. This is really all you need to do, right here. 0.5 times 24.5, divide the whole thing by 298 is equal to 1 times V2 divided by 265. This is good enough as an answer. If you want to work it out a little bit more, make sure you get to here and you're good for the points. If you want to work it out a little bit more, you want to maybe multiply these guys up top by each other, and multiplying by this, do a little bit extra step, but you don't have to actually get an answer. You're not going to have a lot of room in your booklet to do an answer. So this right here is what you're looking for. 0.5 times 24.5 divided by 298 equals 1 times V2 over 265, or something like this that still makes sense. 66 through 69 relate to this whole chart here. It says in the late 1800s, Mendeleev, the Russian guy who developed the periodic table, developed a periodic table of the elements known at that time. Based on the pattern in his periodic table, he was able to predict properties of some elements that had not been discovered. That was my favorite part of the story, as you remember that he yelled at the guy who discovered an element because he said he knew about it first and was somehow correct. It says information about 2 of these elements shown in the table below. So he had these things he called eka-aluminum and eka-silicon. So these kind of pseudo elements that you didn't really know what they were yet. We now know them by different names. It doesn't give us what that name is though. It does give us some information that he predicted and then what the actual value is now that we know what these elements are. 66 says identify the phase of EA element EA eka-aluminum at 310 Kelvin. So right here, how are we supposed to tell what kind of phase this is? So let's see what the chart actually gives us. Density STP, that's really not going to do much to tell us the phase. The melting point could, if we know what temperature it melts at, we could say, well, is it still a solid if it's a lesser temperature than the melting point? If it gets above a melting point, we can assume it melted into a liquid, possibly became a gas if it was really hot. Oxide formula is not going to help us. Molar mass is going to help us. Let's look at this melting point column right here, melting point row. And it says the predicted value was a low melting point, and the actual value was a melting point of 30 degrees Celsius. It wants to identify the phase at 310 K. So this means we have to see what this melting point is actually going to be for this thing, and then compare that to the temperature it stands at here at 310 K to see has it reached its melting point yet where it's going to be a liquid, or is it still below the melting point where it will still be a solid. Unfortunately, we've got K down here and Celsius right here, so we have to convert this Celsius temperature to Kelvin. So to do that, we add 273. So I'm going to do 30 plus 273. That's going to tell me that it's 303 Kelvin as its melting point. So if the melting point is 303 degrees Kelvin, that means if we get it to 303 K, it will go from a solid to a liquid. The question here tells us that we're at 310 K. So is that higher than 303? Has it reached 303 yet? If you're heating this up, which way is it going? By the time it gets to 310 K, it will have gone from a solid to a liquid because it will have melted. Therefore, identify the phase at 310 K. This thing's going to be a liquid. Doesn't tell us anything about the boiling points. We're assuming the boiling point is not just like 2 degrees above it. So that would be a liquid in this case because it has reached its melting point about 7 degrees cooler. 67 says write a chemical formula for the compound formed between EA and Cl. So how are we supposed to know that? The only thing we know about chemical formulas is this oxide formula right now for EA. And it says that EA has 2 ions and the O has 3 when they form this compound. So from that, we can do a crisscross. If we know our compound with oxygen is EA2O3, we can say, well, where did these numbers come from? Let's see. The 2 down here that means we have 2 EAs is because the original charge on the oxygen was -2. And the 3 here for the oxygen is because the original charge on EA is +3. So we now know that EA has a +3 charge as an ion. So we want to see what would the formula be when it combines with chlorine. Chlorine has a couple different options for charges, but if you look at periodic table, the only one that's going to let it pair with this positively charged metal is the -1 charge. And now we can crisscross again. EA gets 1 of them because the chlorine, its number is just 1, and the 3 goes down next to chlorine like that. So our formula is EaCl3. You need 3 of the chlorines with -1 charge each to balance out the 1 of the EA with a +3 charge. So EA1Cl3 or just EaCl3 for number 67. Next question, 68, says identify the element that Mendeleev called eka-silicon, ES. So it's this one right here. and it wants to figure out what element this actually is. He called it ES, silicon. We know by a different name we have to figure out which element it actually is. So what could we actually use here on this chart to help us figure it out? Molar mass, 72 grams per mole, maybe that could be helpful for us. The oxide formula, probably not so much. It tells us that it would have, something, maybe a little bit about what kind of ion it forms. The melting point could be helpful. We have a chart on table S, the second back page of the periodic table, that tells us what things melting points are. We could definitely look that up. The density also tells us that could be helpful. We can always go look up the density of these elements. That's on the same chart, table S. So we can look all these up. If we look up the density being 5.3234 grams per cubic centimeter, if we look up the melting point, that remember we have to convert to Kelvin. So I'm going to quickly grab my calculator here and go from Celsius to Kelvin. I'm going to look at 938 plus 273, and that tells me its melting point should be 1,211 Kelvin. That could be very helpful for us if we're looking up trying to identify the element. And the molar mass, we can also go on the periodic table and see, do we see any elements with a 72 grams per mole molar mass? But all these things, when you add them together and actually look at your reference table, you'll see that the matching element is Ge, which is germanium. That's not how you spell that. Germanium, there we go. So GE is your answer for 68. 69 says show a numerical setup for calculating the percent error of Mendeleev's predicted density of ES. So he thought he could predict what this density was. He's not fully correct, he's a little bit off. So we want to look for a formula now for percent error. It's on the back of his reference table. That percent error formula was the measured minus accepted over accepted, my pen is not working too well today, times 100, maybe it's just me. But in any case, the measured minus accepted divided by the accepted value times 100. So for ES, he predicted that the density was going to be 5.5 grams per cubic centimeter, and the actual value was 5.3234. So his measurement is the predicted one, so we're going to use 5.5 as our measured value, minus the accepted value, the actual value, of 5.3234. We're going to divide the whole thing by the accepted value of, again, 5.3234. Don't forget times by 100 to finish it off. And again, because this question says showing numerical setup, you don't actually have to do the math. As long as you draw something like this, write something like this, it's fine. Measured minus accepted over accepted times 100.
70 to 73 are based on this thing here. It says methanol can be manufactured by a reaction that is reversible. In the reaction, carbon monoxide gas and hydrogen gas react using a catalyst, and the equation below represents the system equilibrium. It says CO, this carbon monoxide gas, plus 2H2 gas can make CH3OH gas plus energy, or you can go reverse, where the CH3OH plus energy add together to produce CO and 2H2. 70 says, state the class of organic compounds to which the product of the forward reaction belongs. So the product of the forward reaction is this guy right here, and just wants us to see which class of organic compounds. So we can go to table R, our organic chemistry chart, and look up and see what does this thing look like. And I see this OH right here, and that, according to our chart, is going to be the alcohols. It also tells us in the question that methanol can be manufactured. So if you see that right off the bat, all that tells you it's an alcohol also. Either way, alcohol for number 70. 71 says compare the rate of the forward reaction to the rate of the reverse reaction in this equilibrium system. As soon as it says equilibrium system, you know one thing, and one thing we know about equilibrium is that the forward reaction rate, I'm just going to shorthand it here, the forward rate is going to be equal to the reverse rate. We know the amounts, the concentrations are constant, they don't change, but the forward rate is equal to the reverse rate. That's what we care about there. 72, explain in terms of collision theory why the concentration of H2 in this system will increase the concentration of C3, why increasing the concentration of H2 will increase the concentration of CH3OH. So explain in terms of, we need to address collision theory in some way. Collision theory said, as the name would imply, that things have to hit each other for reactions to happen. The more times they hit, the better reactions and faster they're going to be. So why does increasing the concentration of H2 in the system make more of the CH3OH? And it's just that because you add more and more of your reactant, they're going to hit the other reactant particles more, and the reaction is going to go faster. So for 72, you can say the more H2 molecules there are, they're going to collide with the CO more. It's going to produce more of the product. You'd say it increases the number of effective collisions. You'd say a greater number of effective collisions occurs. You have to address those collisions because it says in terms of collision theory. So just, all right, more H2 goes to more collisions. And it sure looks like on the answer key, that's technically all you need to say, but just go the whole distance and say more reactions. So you're forming more of the CH3OH. But this is really the key part right there, more collisions. 73 says state the effect on the rates of both the forward and reverse reactions if no catalyst is used in the system. So if you remember, catalysts just speed the whole thing up. They give an easier pathway for a reaction to occur. They help with the energy. If no catalyst was used, the whole thing, as opposite of that, would just go slower. So for each one, rate of forward reaction and rate of reverse reaction, each one goes slower. You could also describe it as a reaction, the rate decreases. Catalysts make it go faster, so no catalyst would make it go slower. All right, 3 quick questions about an organic compound. It says fatty acids, a class of compounds found in living things, are organic acids with long hydrocarbon chains, and linoleic acid, an unsaturated fatty acid, essential for human skin flexibility and smoothness. Formula below represents molecule of linoleic acid. Great. Not really important for the most part here, really at all. Lots of extra detail we don't need to know. All you need to know is this is linoleic acid. That's the only important thing here. It says the formula represents linoleic acid. They had all those words up top just to distract you. Otherwise, just this is what this thing looks like. Great. Thank you very much. Let's answer some questions. 74 says write the molecular formula of linoleic acid. You just got to count all these things. It's a pain. It takes time. You just got to actually go through and count up your C's, count up your H's, count up your O's. I would just kind of check them all for yourself as you go. So you go like 1, 2, 3 H's like that. Make sure you're not missing anything. Double check it definitely because it's very easy to miss something. Just make sure you're doing it right. I'm not going to actually sit here and count it because I've got the answer key. I did it last year. I don't really feel like doing it again. So I know if I went and counted these, I would have 18 carbons. I would have 32 hydrogens. And I would have 2 oxygens. Make sure you double check that, but that's what the key says for me. So I'm going to go with that answer. That's my molecular formula. Number 75 says identify the type of chemical bond between the oxygen atom and the hydrogen atom in the linoleic acid molecule. So the type of bond between the oxygen atom and the hydrogen atom. That means I have to have an oxygen and hydrogen bonded somewhere, and I see it right here. There's only 2 oxygens, so the oxygen and hydrogen right there, that's the only place I have an oxygen and hydrogen bond. So it says identify the type of chemical bond. A couple different options here. They're both nonmetals, so you could just write covalent. Nice and easy. You could say it is a little more detailed, say it's a polar covalent molecule. Covalent is really an important word. But you could say it's a polar covalent because it is. And that's really what you want to go with. I mean, if you say single bond, that's really not, that's a number of bond, but it's not the type of chemical bond. So use the word covalent and you're good. 76, on your diagram in your answer booklet, circle the organic acid functional group. That means in your answer booklet, there's going to be a picture of this big molecule, and you have to circle part of it that represents the functional group. Functional group are those things on table R. It's the extra pieces, and it tells us right in the question, it's an organic acid. So the functional group from an organic acid, as table R tells us, looks just like this. It's a carbon at the end of a chain with a double bonded oxygen and then an OH. So all you have to do is now go to this molecule up top and circle the carbon with the double bonded oxygen and the OH. So I'm going to circle right here on the end. There's our functional group. Notice I'm circling past the bond here of the last carbon. If you cut it off here, that's fine. If you include that bond, just don't go this far past the other carbon. It's just that last carbon there. Really, even if you went like this and circled like avoid the carbon, but you want this whole last piece, really, include everything there. That is your functional group for the organic acid. All right, the next couple of questions refer to this little reading thing plus this picture. It's going to take a couple of slides because it's a big thing, so I'm not going to even bother with it here because we don't need this to read anything of this picture or this writing thing here to answer number 77. I'll do it in a second. Number 77 says just balance the equation in your answer booklet for this reaction that they give you, and it'll look just like this at the bottom. with these blank spots. You know how to do this. We want to add up how many H's and O's on each side. So I'm going to write right here H's. There's 2 to start with, and O's, there are also 2 to start with. On the right side of the arrow, we have 2 H's also, but O's we only have 1. So right now the H's are balanced. I'm going to balance my oxygens. I've got 2 on the left, 1 on the right, which means I'm going to multiply this guy over here by 2. This now gives me 2 times 2 is 4 hydrogens, and 2 times 1 is 2 oxygens. As of now, my oxygens are balanced, but now my hydrogens are unbalanced. So to balance them out, I'm going to multiply the hydrogen on the left side by 2, and that now gives me 2 times 2 is 4 hydrogens to balance out the 4 hydrogens on the right. The oxygens are still balanced at 4. That is a balanced equation. I'm just for good measure going to write a 1 here for myself. I would suggest you do the same. I'm going to tell you right now, as I've told you all year, just write the 1. Don't leave it blank. We've had in the past proctors who don't know what they're doing and tell the kids don't leave anything blank, and then they write something in there. Just write the 1 so everybody knows you meant to put something there. You know you put something. We know you meant to do it. Just write the 1. Never, ever, ever draw 0. 2, 1, 2. You can't reduce those numbers any further. So 2, 1, 2 is your answer for this balancing. Again, there's a long paragraph here. You should read it. There's a picture. You should pay attention. I'm not going to bother because I know what's required of this question, and you don't actually need that to answer these questions. So I'm not going to waste your time and mine by reading this whole thing. Number 78 says, determine the change in oxidation number for oxygen in this operating fuel cell. It gives you the equation right up here. So it's got oxygen by itself, 1 element, no charge. That is a 0 oxidation number. And on the right side, oxygen as part of water has to have an oxidation number. We know the charge of oxygen is going to be -2 because that's the rule for oxygen. Therefore, oxygen goes from 0 to -2, and that's your answer. You could write 0 as a number. You could write the word 0. You could write -2. You could write 2 minus. You could write the words -2. That's your answer for number 78. Number 79 says, state the number of moles of electrons that are gained when 5 moles of electrons are lost in this reaction. Once again, has nothing to do with the writing, has nothing to do with the reading passage, has nothing to do with the diagram. It says 5 moles of electrons are lost. So how much are gained? You have to have the same number of moles being lost as being gained. So if 5 moles are lost, we know 5 moles also are gained. As I said, I know from doing this before that reading has nothing to do with these questions to answer, but just make sure you are reading everything on the test, because usually it does have everything to do with it. In this example, it didn't, so I don't want to waste my time, but you should be reading through and making sure every bit of information is there. Questions 80 to 82 refer to this thing. We've only got 80 and 81 on this page because 82 needs a little bit more space. But it says, in a lab investigation, a student compares the concentration and pH value of each of 4 different solutions of hydrochloric acid, HCl, as shown on the table below, and gives their low data table, each solution, the concentration, and the pH value. 80 says, state the number of significant figures used to express the concentration of solution Z. So we're looking at solution Z right here. The concentration is 0.0010, lots of zeros, and it just wants to know the number of significant figures. So we're going to look at this, and if you remember the significant figure rule, is a decimal present or absent? I see a decimal point right there, so the decimal is present. So I'm going to look at this number from P for present, P for Pacific side. So I'm going to look at it from this side, from the left. And as I go through this now, I'm going to ignore any numbers that are not a non-zero. So I'm going to ignore this 0, I'm going to ignore this 0, I'm going to ignore this 0, and I finally get to a 1. At that point, it and anything after it is significant. So the 1 and the 0 after are the significant figures. So I have 2 significant figures in this number. If there was no decimal, I would start looking at it from the right side, from the Atlantic side, A for absent, A for Atlantic, and I would have, again, once I see a non-zero, anything after that are all significant. Number 81 says, determine the concentration of an HCl solution that has a pH value of 4. So I'm going to erase my ink here. It doesn't show us a pH value of 4, but 4 would go right here on our list. And if you notice any patterns here, every time we go from pH 0 to 1 to 2 to 3, the decimal place just keeps moving one place to the left. So it moved one place to the left here between 0 and 1, and then moved another place after 1 to 2, another one from 2 to 3. So to go from 3 to 4, I'm just going to move it one more place to the left, and that gives me 1, 2, 3 zeros, 1, and then another 0. That's your answer right there. 0.0001 0 as your concentration. It's one more 0 after the decimal place than in concentration or pH value number 3. Just look at the pattern. There's no math to be done here. It shows you this trend. You can see it goes like a little triangle shape here. Every time you change and go up one pH value, your decimal place moves one to the left. So 4 is the next one. If it was 5, you could just do it 2 more times. But this is your answer right there for pH 4. 0.00010 is your concentration of HCl. Number 82, same table. It says determine the volume of 0.25 molar NaOH, a base that would exactly neutralize 75 milliliters of solution X, which we know is the acid HCl. So neutralize means we're adding acid and base, and that's going to be our neutralization formula, our titration formula. Remember we did the thing with the burettes, adding acid and base to each other, and we need this equation right here. Now I did give you the little modified equation we used during the year, where because some acids and bases have different numbers of H's or OH's, we have to change the numbers a little bit. We don't have to worry about that here because the base only has one OH in it and the acid only has one H in it. So we're going to use this exact formula we're given here. Otherwise, we would have done that thing where it's the number of H's times the MAVA and then the number of base of OH's in the base times the MBVB. Don't have to worry about that here. So I'm going to plug some numbers in here. I've got, what is I'm looking for? I'm looking for the volume of base, so that's my VB, that's going to be my unknown, so I have to know everything else. My molarity of acid, it says we're looking at solution X, so that's what I'm looking at right here. My molarity of acid is going to be 0.10 times the volume of acid, it says is 75 milliliters, and that's going to be equal to the molarity of the base, which it tells us is 0.25 molar, times the volume of base, the VB, which we do not know, that's our unknown that we're looking for. So I'm going to multiply everything on the left, and 0.10 times 75 is going to be equal to 7.5. And then on the right, it's 0.25 times still VB. I didn't change anything. I want to get that VB by itself, so I divide by 0.25 over here. Cross out. I divide by 0.25 on the other side. And 7.5 divided by 0.5 will give me the volume of base needed. And my math tells me that that's going to be equal to 30 milliliters of base. So the base is about a little more than twice as strong. It's about 2.5 times as strong, 0.25 compared to 0.10 for the acid. So you have a volume of base needed that's the opposite. That's a little less than half of that, 30 compared to 75. The base is stronger, so you need less of it to balance out more of the weaker acid. Last 3 questions. It says carbon dioxide is slightly soluble in seawater. As carbon dioxide levels in the atmosphere increase, more CO2 dissolves in seawater, making the seawater more acidic, yada, yada, yada. Seawater contains aqueous calcium carbonate, which is used by some marine organisms to make their hard exoskeletons. Don't really need any of this. It's just the graph is showing you the comparisons between pH of the seawater and solubility of CaCO3. So how much CaCO3 is dissolved in the seawater, and what does that mean for its pH? Number 83 says, state the trend in solubility of CaCO3 as seawater becomes more acidic. So as seawater becomes more acidic on this graph, what happens to the amount of CaCO3 that dissolves? Trick here is you have to see it becomes more acidic. That means we're actually reading it towards the left because acidic is lower numbers. That's the trick here. If you're reading it from left to right saying, oh, it's, as time goes on or something, you're not going to get this right. It's saying as your pH becomes lower. So as you're looking at this line from left to right, what happens to solubility? And it shows here that the solubility is going to increase. The solubility is going up. This line is going up as you move from right to left with the decreasing acidity, or the increasing acidity, the decreasing pH. So solubility is going to increase. That's the trend as we get lower and lower pHs. 84 says, state the color of brown crystal green in a sample of seawater in which the CaCO3 solubility is 10 to the negative 2 molar. Now for this, it talks about brown crystal green, so we're going to need our indicator chart. I'm going to go ahead and erase these arrows again. And it says the solubility of CaCO3 is 10 to the negative 2 molar. So we're talking about right here. To use this, though, we need to see what our actual pH is. So we're going to just follow this right over the line. And it hits right about there. And our pH is somewhere north of 6. It's not yet at 7, which would be right there. But it's important. Let's say it's like 6.5 or so. pH in the somewhere 6.5-ish range. We want to look at the indicator brown crystal green. And brown crystal green right here says it changes color between pHs 3.8 and 5.4. So this 6.5 will be well above the 5.4 where it has already changed color. And anything to the left of 3.8 would have been yellow. Between 3.8 and 5.4 is going from yellow to blue. Anything more than 5.4, it is already well and good blue. So at a pH of around 6.5, brown crystal green will definitely be a blue, solidly blue color. Last question 85 says a sample of seawater with a pH of 8 has a pH of 8. Determine the new pH of the sample if the hydrogen ion concentration increases by a factor of 100. Remember that the pH scale is a logarithmic scale, which means every time you change one pH unit, it's actually a 10-fold change in concentration. So if you're becoming increasing the hydrogen ion concentration, you're becoming more and more acidic. So going from, let's say this is a 7 in here and a 5 in here. If you're going from an 8 to 7, that's a 10 times increase. Going from 7 to 6 is another 10 times increase. Going from 6 to 5 is another 10 times increase. So if you were increasing by a factor of 100, it means you made 2 moves. You made one move was a 10-fold increase, and another move would be 10 times 10 is a 100-fold increase. So increasing by a factor of 100 means you changed 2 pH units to the left. So you went from 8 once to 7, and then down, and you ended up at 6. So your pH would be 6. That is a 100-fold increase in the concentration of the hydrogen ion concentration. You become 2 smaller pH units from 8 to 6. That is your Regents. You are done. Now go study and do the exact same thing on yours.